Hi, I'm Engineer Febus Reidj Cruz from Mapua University, School of Electrical, Electronics, and Computer Engineering. I hope that you are having a great day. In this video, you will know how electronic current flows and how it is produced in semiconductor materials. The transport of free electrons supplies the electron current, while the transport of holes gives the hole current. Both electron current and hole current contribute to the current in the semiconductor. When there is an applied voltage or electric field, the flow of carriers is called drift current. Drift current is the amount of current in response to the applied voltage or electric field. There is another way to produce current in a semiconductor. Even without voltage or electric field, the charge carriers in semiconductors move from regions of higher concentration towards the areas with lower concentration. This flow of carriers, due to concentration gradient, is the diffusion current. The amount of electron drift current in semiconductors is IN drift and is equal to the product of mu n, E, A, N, and Q. IN drift is electron drift current in coulomb per second or ampere. Mu n is the mobility of electrons, and for silicon it is 1,350 square centimeters per volt second. E is the electric field, the applied voltage divided by the length of the material in volt per centimeter. A is the cross-section area of the semiconductor where the electron current is flowing in square centimeters. N is the density of electrons in electrons per cubic centimeter. And Q is the charge of electrons, and 1 electron equals 1.6 times 10 raised to negative 19 coulomb. The amount of hole drift current is expressed as IP drift and is equal to the product of mu P, E, A, P, and Q. IP drift is the hole drift current. Mu P is the mobility of holes, and for silicon, it is equal to 480 centimeters squared per volt second. E is the applied electric field. A is the cross-section area of semiconductor material. P is the density of holes. And Q is the charge of holes. And 1 hole equals 1.6 times 10 raised to negative 19 coulomb. Drift current is the amount of current in semiconductors as a response to an applied voltage or electric field. The electric field accelerates the charge carriers, and the total drift current is the sum of free electron drift current and hole drift current. The drift current depends on the mobility and density of carriers, and on the applied electric field and cross-section area. Mu n is the mobility of electrons, and mu p is the mobility of holes. N is the density of electrons, and P is the density of holes. E is the electric field, A is the cross-section area, and Q is the charge of carriers. Both electron and hole are equal to 1.6 times 10 raised to negative 19 coulomb. The drift velocity describes the speed of carriers moving in a current under an electric field. The velocity of carriers at a lower electric field directly depends on the applied electric field and is equal to the product of the low field mobility of carriers and the electric field. At a higher electric field, the velocity of charged carriers no longer increases linearly with the electric field. This is because the charged carriers collide with the lattice more frequently. They cannot accelerate much. The limitation is the velocity saturation of carriers under a higher electric field. This figure shows the saturation of carrier velocity at the higher electric field. At 1 megavolt per centimeter, the velocity of carriers in silicon equals 9.93 million centimeters per second. There is another way to produce current in a semiconductor. Even without voltage or electric field, the charge carriers in semiconductors move towards the areas with lower concentrations. This flow of carriers is the diffusion current. The total diffusion current is the sum of free electron diffusion current and the hole diffusion current. The diffusion current depends on the gradient in free electron concentration, dN over dx, and on the gradient in hole concentration, dP over dx. The N is the concentration of free electrons, P is the concentration of holes, and X is the size of the semiconductor. D is the diffusion constant. In silicon, diffusion constant of free electrons, dN, is 34 square centimeters per second, while the diffusion constant of holes, dP, is 12 square centimeters per second. A is the cross-section area and Q is the charge of the carriers. In summary, the total current in semiconductors is the sum of drift currents and diffusion currents. The free electrons and holes travel in semiconductors as drift currents when there is a voltage or electric field. The free electrons and holes also flow as diffusion currents when there are gradients in the carrier concentrations. The amount of current in semiconductors is also defined in terms of current density, which is current flowing through a given cross-section area. The ratio of diffusion constant over the mobility is proven to be equal to the thermal voltage. This is referred as the Einstein relation. In summary, the current in the semiconductor is produced by the flow of free electrons and holes. These are charge carriers, move when there is an applied voltage yielding the drift current. Also, even without voltage, these charge carriers move whenever there is a concentration gradient, creating the diffusion current. Before we end this video, please allow me to encourage you to appreciate your studies and enhance your creative and innovative ideas. Keep going with this series on basic physics of semiconductors. Thank you and see you again in the next videos. Thank you very much.